And in this one, it asked me to find the vertex using the old opposite of b over 2a. So for this guy, opposite of b is a -4 all over 2 times a, which is a 1. So that gives me a -4 over 2, which is a -2. And now to find the second half of this vertex, I have to plug that back in. So I plug it in to find the y value. And when I do that, I end up with y equals 0. So the vertex here is the ordered pair -2, 0. So then the second part of this question asked me to find the x intercept, or the x intercepts, by plugging a 0 in for y. So here, if I plug a 0 in for y, I'm going to solve this for x. I want to find the x intercept. So I'm going to solve by factoring, so I build a bridge. Two numbers that multiply to a 4 but add to a 4 or a 2 and a 2. And I get to use my shortcut on this one and everything. So that's the this guy factors into an x plus 2 times x plus 2. And again, equals 0. And I said each factor equals 0. X plus 2 equals 0. Here, x plus 2 equals 0. And I could solve each of these. This one I subtract 2, and I get x equals -2. This one, I'm obviously going to get the same thing. So really, I get one answer. And the answer is the ordered pair -2, 0 for my x-intercept. So I found two different things. And normally, these things are not the same. But this time, they are. So I got the vertex -2, 0. The x-intercept is also -2, 0. So what's implying here when it says what did the results mean, it means that this time the vertex is the x-intercept. All right. In other words, we have a graph that kind of looks like this. Okay, we have the vertex is the spot on the x-axis. Okay, so the only part of the parabola that touches the x-axis is the vertex. Okay, so vertex on x-axis. Okay, and that's the interpretation piece. The next one, it asked me to just multiply or simplify here. So this one's my distributive property. So I distribute that 2x. I'm going to distribute that 2x to each of these. And then I'm going to distribute the +1 to each of these. So when I distribute the 2x, that gives me a 2x cubed plus 4x squared minus 8x. When I distribute the 1, that gives me a plus x squared plus 2x minus 4. And that's just combining like terms. The 2x cubed doesn't have a like term. The 4x squared and the x squared gives me a plus 5x squared. And then these guys give me a minus 6x, and the minus 4 just tags along for the ride. Okay. The next one, same kind of thing. But remember, when we square a binomial, it's 4x plus 5 times itself. So 4x plus 5 squared is 4x plus 5 times 4x plus 5. Here I have to distribute or FOIL this time because I can't just square each piece. Okay, and that's the common mistake that students make. So here I distribute the 4x, and then I distribute the 5. So when I distribute the 4x, that's a 16x squared plus 20x. When I distribute the 5, that's a plus 20x and a plus 25. And then combine like terms. 16x squared plus 40x plus 25. And that's it. For these guys, these are the literal equations where we're just rearranging them. We're isolating one of the variables. So this time we want to get b by itself. So for this one, I want to get this b right here by itself. And really this is addition. So I can think of this as mx plus b, or I can think of it as b plus mx. In order to get the b by itself, I just have to subtract that mx from each side. And so when I do that, I find out that b equals, well, y minus mx. I can't combine any terms there. They're not like terms, so I just leave it as y minus mx. I literally leave it in terms of the operations, okay? I literally leave it the way it is. That's why they're called literal equations, because we're being literal about the arrangements of these things. This guy, same kind of thing. To get rid of that 1/3, I'm going to multiply each side by 3. Because remember, to get rid of any fraction, I can always get rid of a fraction by multiplying by the common denominator. So I get 3v equals bh. And now if I want to solve for b to undo that multiplication, I just use division. And so now I get b equals, this guy, leave it the way it is, 3v over h. Okay, just leaves it as a big giant fraction. Okay. The next one, we're using the graph to identify certain things, and really if it looks like it goes through a certain point, just assume it goes through that exact point, okay? We're not going to try to trick you in terms of having it some be obscure decimal for this one. So this guy, the vertex is this point right here, which is the ordered pair 2, 3. And then the axis of symmetry, remember the axis of symmetry is always x equals the x value from the vertex. You can see it on the graph. The mirror image of this thing is right here. That's the line that cuts this thing in half. And that's the equation x equals 2. And then the next question, is the vertex a maximum or minimum? Well, the vertex is at the very bottom of this thing, so that is a minimum value. The y-intercept, we can see where it crosses the y-axis, is right here. And that looks like the ordered pair 0, 7. The domain, because the arrow's on each end, I just say, hey, how far left and right does this thing go? So to the left, it goes all the way to negative infinity, so it starts at negative infinity. And to the right, it goes all the way to positive infinity. So domain is negative infinity to positive infinity. Remember, parenthesis for each, because you can never actually equal infinity. The range then, start at the bottom and work your way up. It looks like the lowest point on this parabola is a y value of 3. So it starts at 3, and then parabola opens up from there, so it heads towards positive infinity. And this one actually equals the 3. It touches a y value of 3, but you can never actually equal infinity, so we use a parenthesis. This one used the graph to determine whether there is a stretch or compression. So we kind of got to look at the shape of this thing. As I kind of investigate the shape, counting from the vertex, you start at the vertex, it's over 1 up 1 to get here, and then over 2 up 4 to get here. So that's my standard shape. Remember, over 1 up 1, over 2 up 4, over 3 up 9, over 4 up 16. So this one's not stretched or compressed. It's neither of those. This is the standard shape. If it was stretched, those values would be higher. They'd be multiplied instead of 1, 4, 9. If it was a 2, it would be like 2, 8, 18, that kind of stuff, okay? And if it was a shrink, then it would be, or a compression, and then the values would be shrinking. And then this one, state the number and type of solutions of the quadratic. Well, the solutions are the x-intercepts. When you look at the graph, there are no x-intercepts, which means there's no real x-intercepts. It doesn't actually cross the x-axis, which means the x-intercepts must be imaginary. Well, the solutions that we consider imaginary would be complex solutions, and they always come in pairs. So this one would have 2 complex solutions. And even though I don't even have the equation to be able to check that like I would with the discriminant, I know that's what kind of values it's going to give me because it doesn't actually cross the x-axis, okay? This one, state the domain and range, draw a sketch if you need to. And again, you know, these don't have to be real involved sketches, so like something like this guy, it's got a y-intercept of 5 and then a slope of 1, kind of looks like that. It's the equation of a line. And see, lines are nice unless it's vertical or a horizontal line. We're going to kind of end up in the same situation. For the domain, if I look left, it goes to negative infinity. I look right, it goes to positive infinity. And I use parentheses for each because we can never equal those values. It goes down forever, so it starts at negative infinity. It goes up forever, so it goes up to positive infinity. And again, parentheses because I'll never actually equal those values. This guy, same kind of thing, just draw a quick sketch of the graph. Well, this one has a vertex. This is vertex form, so the vertex is negative 2, 4. And again, I don't have to be real involved with the graph here, but negative 2, 4 is approximately here. The thing opens down because the a value right here is a negative, and it's the standard shape. So just a quick sketch, there it is. Okay, good enough. It's not super accurate, but that doesn't matter. I'm just looking for domain and range. I can now tell that this thing goes to the left forever, negative infinity, and then it goes to the right forever, positive infinity, parentheses for each. But now the domain, it goes down forever, so it starts at negative infinity. But as we work our way up, the highest point on this parabola is at positive 4, because that's where my vertex caps out. And I do actually equal that value, so I use a bracket. But that's it. These guys, the feasible region is given. So I have to state the vertices. Remember, those are just the points of the feasible region, the corner points. So this guy, this guy, this guy, and this guy. So just kind of working my way around this thing. I'll start with 0, 0. The next one I've got 0, 4. I also have 1, 2, 3, 4, 5, 3. And then 5, 0 is the last one. Okay, so those are my corner points of the feasible region. Now, if I want to figure out, all right, if this is the objective function, I want the maximum, the minimum, I just have to plug all these values into the objective function. So if I plug like the 0, 0 in, and then I'll plug the 0, 4 in, and the next point, and just plug in each of them in. And so after I plug each of those in, this guy gives me a 0, this guy gives me an 8, this guy gives me an 11, and this guy gives me a 5. And so the maximum value is the biggest one I have, that was 11. The minimum value is the smallest one I have, which is a 0, and that's it. Okay, so use the objective function, plug in those values, plug in those ordered pairs. This one, Brenda's school is selling tickets to a spring musical. On the first day of ticket sales, the school sold 3 senior citizen tickets and 9 child tickets for $75. The next day, it was $67 they collected, but 8 senior tickets and 5 child tickets. And we want to know how much does each type of ticket cost. So what I'm going to do is for the senior tickets, I'm going to do X, and for the child tickets, I'm going to do Y. Okay. I always pick the simple variables like X and Y. S is not a good variable here. I could use C for child, but S for senior citizen might get messy. So the way it's written, 3X, so 3 senior citizen tickets plus 9Y should equal $75. And then here, 8 senior citizen tickets plus 5 child should equal $67. Those are the two situations they give me. This is a system of equations. I'm going to solve this system by substitution. It looks like this guy is easy to solve. Elimination would be fine here, but I can tell that I'm going to get some smaller values if I use substitution. So here I'm going to subtract the 9y. Plus, I think most of us are pretty well practiced with elimination. Substitution is the one that we might need a little bit of extra work on. And the other thing I notice is that first equation is all divisible by 3. So I get x equals a negative 3y plus 25. And so now I can plug that into the other equation here. So a little space. So right here, I've got 8 times. That's going to be a negative 3y plus 25 plus 5y equals to 67. And now I distribute. That's 200. I'm going to subtract that 200 from each side. And at the same time, I'm going to go ahead and combine those like terms. So let's see, I got a negative 19y equals a negative 133. And now I divide. And so I find my y value. My y value ends up being, looks like a 7. But now I have to come back over here, right here, x equals negative 3 times 7 plus the 25. I can plug it back in and find the x value. It looks like the x value is a 4. Okay? And so for the senior tickets, $7. For the child tickets, it's $4. Or no, sorry, other way around. Senior tickets are $4 and the child tickets. And that's the only disadvantage to using variables like x and y is sometimes we lose track of which one is which. This time the senior tickets was the $4 and the child tickets was the 7, okay, for x and y. All right. This one, it says to write the standard form equation of the quadratic. And so again, you think about quadratics. Normally when we solve a quadratic, we start with something in standard form. We start with y equals ax squared plus bx plus c. That's standard form for a quadratic. And then when we're solving to get things like x, we would build a bridge and we would factor this thing. And then we'd set each factor equal to 0, and then we'd get our 2 answers. So we kind of work backwards. If we had like x equals 4 and x equals a negative 5, that means I would have had the factor like x minus 4 equals 0. See, because to get that, I would have had to add that 4 to each side. Likewise, over here, this would have to be x plus 5 equals 0 to give me an answer of x minus 5. See, I'm just kind of working my way backwards. And that means I would have had the factored form of this thing as x minus 4 times x plus 5 equals 0. And then if I multiply this out, if I FOIL, if I distribute, that gives me x squared plus 1x minus 20 equals 0, which means I must have started with the equation y equals x squared plus x minus 20. And see, now to find the x-intercepts, you would plug a 0 in for y, and then you'd solve by factoring. We're just working backwards. So if I give you two solutions, just rewrite them as factors, multiply those factors out, and you have your equation of the parabola in standard form. Okay? These guys says state the solutions of the equations. Leave your answers as reduced fractions. Really, this is solving by factoring, but all the factoring is done for us. If it's factored and equal to 0, just set each factor equal to 0. X minus 2 equals 0, x minus 3 equals 0. Here I add the 2 to each side, so I get x equals 2. Here I add the 3 to each side, so I get x equals 3. And that's it. This one, same kind of thing. I set each of these equal to 0, so I do x equals 0. And then I do the 2x plus 9 equals 0. And see, this one's already solved, x equals 0. That one's done. This one, I'd have to subtract the 9 from each side. And then I'd have to divide each side by the 2. So I'd get a negative 9 over 2. Again, just leave it as a fraction like that. We're good to go. This one, I would do the 2x minus 1 equals 0. And then I'd do the 5x plus 4 equals 0. And I'm fairly confident most of us can solve this from here. Add the 1. I'm not showing all the little steps. And then divide each side by the 2. And if you're still somebody who's having trouble with something like this, actually show the division, and then it's really easy to see this is 1 over 2. Okay? Same thing here. You subtract that 4 from each side, and then divide by the 5. That's a negative 4 over 5. But again, show that little step divided by 5. Well, now I can see it's negative 4 over 5. The next one, find each value and graph. So this one, the vertex, since this is in standard form, to find the vertex, I do opposite of b over 2a. 6 over 2 is a 3. That's the x value for my vertex. I have to plug it back in to get the y value. So I'm going to plug this guy back in. So let's see, that's a 9 minus 18 plus 8. That's a negative 9 plus 8, which is a negative 1. And so that's my vertex. Axis of symmetry is always x equals the x value from the vertex, so x equals a 3. The y-intercept, I just have to plug a 0 in for x. If I plug a 0 in for x, and that one's easy enough to do in our heads, but let me show it, I guess. 0 squared minus 6 times 0 plus 8. It's like 0 plus 0 plus 8, which is 8. Okay. And then the x-intercepts, I have to plug a 0 in for y this time. If I plug a 0 in for y, I get 0 equals x squared minus 6x plus 8. I have to solve this by factoring, build a bridge. This guy factors into an x minus 4 and an x minus 2. And then I set each factor equal to 0. X minus 4 equals 0. X minus 2 equals 0. And I solve each. Here I add the 4. Here I add the 2. So we get two x-intercepts. One's a 4, 0, and the other one's a 2, 0. And then maximum or minimum, just looking at the a value of this thing, the a value in this guy is a positive 1, which means this parabola is going to open up. Well, if the parabola opens up, it means my vertex is going to be at the bottom. It's going to be a minimum. And if I go ahead and plot all this stuff, it should confirm that. So let's see. 3, negative 1, that's right here. I've got my axis of symmetry, which I can draw if I would like. The y-intercept, 1, 2, 3, 4, 5, 6, 7, 8 is way up here somewhere, a little off the graph, and I can reflect that point over here as well. The x-intercepts of 4, 0, and where were we? 2, 2, 0. Oh, I plotted that at 5 like a weirdo. Let me try again. And so when we look at this thing, we can kind of see the shape of this. And we can use that a value as well, standard shape, over 1 up 1, over 2 up 4, to kind of fill in the gaps a little bit. Yeah, that's it. And now we can see the vertex is a minimum. It's at the bottom. All right. These guys, when you're plotting absolute value, remember absolute value, when you're graphing this thing, is a V. So we need the vertex. And remember, this is in vertex form, so it's opposite of this guy just as it is. So we do the 1, positive 3. So 1, 3 is right here. And then we look at the A value. This thing's going to open down because the A value is a negative. See right here, that negative 2. So it opens down. And then we use that A value kind of like the slope. Okay, so down 2 over 1, but in each direction to make my V. Down 2 over 1, but in each direction to make my V. And that's kind of how we use that stuff. And there it is. Same thing with the next one, the vertex. It's opposite of this guy just as it is. So that's negative 3, negative 4. The A value this time is 1, so this one's going to open up. And we're going to use that 1 kind of like the slope. Okay, so negative 3, negative 4 is down here. It opens up with a slope of 1, up 1 over 1, up 1 over 1 in each direction. That's it. The next one, again, opposite of that guy, the other guy just as it is. So this is the ordered pair 1, 4. This one's going to open up because the A value is positive, and we're going to use that 1/3 kind of like the slope. So now I plot this thing 1, 4. It's right here. Opens up with a slope of 1/3, so up 1 over 3 in each direction. Okay? 1 over 3. And that's it. That's how we graph those absolute value guys. All right? This one, very similar, but this time it's going to be a parabola because it's an because it's a squared thing. Absolute value is a V. Parabolas are that U shape, but really we approach it the same way. Vertex form, it's opposite of this guy, so that's a 3. And then the other guy just as it is, that's a 4. Axis symmetry is x equals the x value from the vertex. The y-intercept of any function ever, you plug a 0 in for x. And this one is a little bit more difficult to do that than standard form was, but we plug it in. See what happens. Negative 3 squared. So now I have negative 1/2 times 9. That's a negative 4 1/2. Plus 4 is a negative 1/2. Let's go to pair 0, negative 1/2. The x-intercept of any function ever, you plug a 0 in for y. So this time if I plug a 0 in for y here, and I'll solve. I subtract that 4 from each side, and I will actually show all the little steps in here since this is a little bit more of a complicated one. See, I'm getting that thing that's squared all by itself here for a moment. Scroll down a little bit so I can do my work. Now to get rid of that fraction, I'm going to multiply each side by negative 2. And now from here, I'm going to take the square root of each side. And I'm actually going to simplify this thing. There's really no need in this particular example. I'm going to simplify that square root, even though I don't have to, because I'm going to be plugging this thing into my calculator anyway. But anyway, if I take the actual square root, if I simplify that, that's going to be a 2 root 2. And now I'm going to add that 3 to each side. And the reason I say there was no need to really simplify that is because when I'm talking about x intercepts, it's really silly to leave my answer like this. Okay? If I just said solve, I would leave the answer like this. But really, for x intercepts, I want to plug this into my calculator. I want to get some decimal approximations. And when I do that, when I plug one version in, the plus, when I do the plus version, I end up with a 5.83. When I do the minus version, I end up with a 0.17. So that's kind of how I want this thing. And really, you can do one decimal place would even make the most sense here. Say 5.8, comma 0. And then 0.2, comma 0. Because as I go to graph this thing, that's about as accurate as I'm going to be able to be anyway. Okay? And then maximum versus minimum, I see my A value is a negative, so this thing's going to open down, which puts my vertex at the top as a maximum. And I'll confirm that as I go to graph this thing. So let's see, 3, 4, right here. 0, negative 1/2 is right here. Oh, I've even got my axis of symmetry, I suppose. So I can reflect that point over here. The X intercepts I can even plot. Let's see, 5.8 is right here, and 0.2 is maybe right here. Okay, so really close to those values, and I can kind of see this thing taking shape. I can even use the A value. Remember, the standard shape is, if we're opening down, would be over 1, down 1, over 2, down 4, over 3, down 9. But go half those. Over 1, down a half. Instead of over 2, down 4, I go down 2. It's half of that. Okay. Instead of over 3, down 9, I go down half of that, 4.5. And that confirms my value there. Over 4 is down, instead of 16, down 8. Okay. And so I kind of get this nice slightly wider parabola than I have. Okay, that's it. This guy, which pair of inequalities being illustrated by the graph? First of all, when we look at this guy, this dotted line is a vertical line, which means it's an x equals type of equation. And since that is an x equals type of equation, we're looking for the ones that have like these x equals type things in them. Okay, and so when you look at something like this guy, that kind of fits that mold. This guy does not. So right away we can get rid of letter C, because y equals would be a horizontal line. So we can kind of toss this answer. Okay. The rest of these all say x is less than, which kind of fits. So then we just got to look at this guy. And when I look at this thing, this guy has a y-intercept of positive 2, and it has an x-intercept of negative 2. So kind of just look at each of these and kind of do the cover-up method like here. So like here, if I were to plug in, there's an x value of 2. So it can't be this one because we need an x value of negative 2. Okay. If I look at this guy, again, x value of 2, we need a negative 2. All right. And so when I look at this guy, here's an x value of negative 2. If I were to plug a 0 in for x and solve for y, I'd have to divide by the negative. I'd get a y value of positive 2. That's the equation of this line. It's got to be letter D. So using a little bit of process elimination, kind of trying to graph each of those things should give us the result we're looking for. Okay. This one, it says how many solutions does each system have? If there's one, find the solution. So really all we're going to do is solve each of these and see which ones give us no solution, and infinite solutions, which one gives us one answer. Okay. So like this guy, the way it's set up, I would solve this by elimination. Okay. I'm going to eliminate the x value, so I'm going to multiply this second equation by 2. All right, set up nicely for that. I chose the x because I have to multiply by something smaller. So it's a negative 2x plus 2y equals a negative 2. And now if I add that top equation, that bottom equation, kind of ignore that one in the middle that was the one I modified. But if I add these up, I end up with a negative y equals, looks like a negative 14. And I would divide each side. And right away, I know I'm going to get one solution now. My y value is a 14. So now you just have to plug that back into either one of these. And hopefully you can do that kind of in your head, or you can take it off to the side and do it. But if you plug that back in, it looks like I get a 15. Okay. So this one has one solution, and it's the order pair 15, 14. Okay. The next one I would solve by substitution. I already have y equals this, so I'm going to substitute that in for y right here. That's a negative 4x plus 2 going in for y. And I'll just combine like terms. The x's cancel, I get 2 equals 2. Well, when you get a true statement, that means we have infinite solutions. Okay. And the last one here, I would solve this one by substitution as well. Y already equals the 3x minus y. So I'm going to plug that into that top equation. 3x minus y equals the 3x minus 7, sorry. So I plug it into that top equation. Combine like terms, the x's cancel, I get negative 7 equals 2, which is a false statement. That does not equal. That's when it's no solution. So if all the variables go away, it's either infinite solutions or no solutions. Look to see if you have a true statement or a false statement. Okay. This one, it asks if 4, 1 is a solution to the system. I just have to plug it into each of these. So like I plug it into the first one, and it looks like I get 4 plus 5 equals 9, which is a true. So 9 equals 9, which is true. Okay, but it can't just work for one of them, it has to work for each of them. So I gotta plug it into the next one as well. So here I get 16 plus 17, which is a 33. And 33 does not equal 17, so I would say no, this is not a solution to the system, okay, because it only worked for one of the values in there, okay. This one, it says describe the graph of the system of equations, okay. So if it has one solution, it means they intersect at only one point, okay. So they intersect at one point. And, you know, this could be, you know, two lines that intersect at a point, kind of looks like this. And that point of intersection, this is the solution, all right? I guess it could be a parabola, and maybe like something like a vertical line, and that would only intersect at one point as well, all right? Two solutions means they intersect at 2 points. Remember, when we're looking at the graph, the solution is where they intersect. So like this would be something like maybe a parabola with a line going through. Notice there's two solutions here. Infinite solutions is when basically it's the same equation graphed twice, all right? So it's the same graph twice, and really it means all of their points intersect, and that's the situation where we have one line, and then the other line is that same line graphed on top of it, so they share all the points, all right? And then no solution, this is when the graphs don't intersect, okay? And really for the purposes of lines, this is when we have parallel lines. So we have two lines that kind of look like this. Oh, that was terrible. Those don't look parallel at all. Let me try again. I can do better. Okay. This one asked me to graph this guy. So something like this. I just plot it like a line. So y-intercept of 4 with a slope of -2. 1, 2, 3, 4. Slope of -2 is down 2 over 1, down 2 over 1. And because there's no equal to condition, inequalities, I have to use a dotted line for this guy. And then I have to shade one side or the other. Since I'm less than this guy, I want to shade below the line. So I shade everything down here. And then the second piece of this thing, it says, what's a solution? Well, you can pick any point that's in that shaded region. So I might pick the point like 0, 0 as an example. Okay? Or I could pick the point like -3, -1. Okay, so anything that's in that shaded region will work as a solution to this guy. All right. And then these guys graphing. X equals, let me use blue so it shows up a little better on the graphs. X equals 3 is a vertical line. Remember, vertical lines are always x equals, so here's an x value of +3. Then I draw a vertical line. Okay, y equals is a horizontal line. This one I would do the x and y intercept. If I kind of plug a 0 in for y, you can solve that in your head. The x-intercept equals a -2. And again, you know, red is an ordered pair if you're not sure. Red is the ordered pair -2, 0. And then plug a 0 in for x, you can see that the y-intercept is a 3. Now if you just plot those 2 points, -2, 0, and 0, 3, I can even see the slope. It's up 3 over 2, up 3 over 2, and go from there. Okay. The next one's in slope-intercept form. It's got a y-intercept of -3, and it's got a slope of 1/2, up 1 over 2, up 1 over 2, down 1, back 2. And that's probably the easiest version we have for graphing. This one, there's like a +0 here. It's in the format y equals mx plus b. The y-intercept is 0, and the slope is -4, down 4 over 1, or up 4, back 1. This guy, it's in that standard format. Find the x and y-intercept. Find the x-intercept, you plug a 0 in for y, so I get an x value of 4. That's the x-intercept. And now plug a 0 in for x, and if I solve that, that's a -1. That's the y-intercept. And I plot each of those. 4 zeros right here, 0, -1 is right here, and I can see the slope, up 1 over 4, down 1, back 4. I can use that to plot extra points on this thing. Okay. And then this one's in point slope form. This is the one that most of us probably don't recognize, but remember, it's opposite of this guy, opposite of this guy. So it's giving me an ordered pair, and it's the ordered pair 1, -2. So I plot that point. So it's just like slope-intercept form. Instead of starting at the y-intercept, I'm starting at some random point like 1, -2. And now I'm using this slope down 3 over 2, or up 3 back 2. Okay, if you're not sure about that one and you don't remember point slope form, you can always distribute here and then solve for y and put it in slope intercept form. Okay, hope that was helpful and good luck on your test.